Good day, this is the Professor, CBMD PhD, and today's Thursday, May 18th, 2023. It is 9:33 and 13 seconds, p.m. Eastern Daylight Time, and today's research, quantum simulator. So let's up to it here. The scientific investigators research curved space-time in a quantum simulator. Date May 17th, 2023. Source: Vienna University of Technology. The connection between quantum physics and the theory of relativity is extremely hard to study, but now scientists have set up a model system which can help. Quantum particles can be tuned in such a way that the results can be translated into information about other systems which are much harder to observe. And this kind of quantum simulator works very well and can lead to new insights about the nature of relativity and quantum physics. And this is partly because the mathematics in this field is highly complicated. At the same time, it is tough to perform suitable experiments. One would have to create situations in which phenomena of both the relativity theory play an important role, as for example a space-time curve by heavy masses, and at the same time quantum effects become visible, for example the dual particle and the wave nature of light. A so-called quantum simulator is used to get to the bottom of such questions instead of directly investigating the system of interest, namely quantum particles in curved space-time. One creates a model system from which one can then learn something about the system of actual interest by analogy. The basic idea behind the quantum simulator is simple. Many physical systems are similar, even if they are entirely different kinds of particles or physical systems on different scales that at first glance have little to do with each other. These systems may obey the same laws and equations at a deeper level. This means one can learn something about a particular system by studying another. We take a quantum system that we know we can control and adjust very well in experiments. In our case, these are ultra-cold atomic clouds held and manipulated by an atomic chip with electromagnetic fields. And suppose you properly adjust these atomic clouds so that their properties can be translated into another quantum system. In that case, you can learn something about the other system from the measurement of the atomic cloud model system. As much like you can learn something about the oscillation of a pendulum from the oscillation of a mass attached to a metal spring. There are two different physical systems, but one can be translated into the other. In the vacuum, light propagates along a so-called light cone. The speed of light is constant at equal times. The light travels the same distance at each direction. However, if the light is influenced by heavy masses, such as the sun's gravitation, these light cones are bent. The light's paths are no longer perfectly straight in curved space-times. This is called gravitational lens effect. The same can now be shown in atomic clouds. Instead of the speed of light, one examines the speed of sound. Now we have a system in which there is an effect that corresponds to space-time curvature or gravitational lensing, but at the same time, it is a quantum system that you can describe with quantum field theories. And this is not only interesting for generating new data for basic theoretical research, solid-state physics, and the search for new materials also encounter questions that have a similar structure and can therefore be answered by such experiments. They now want to control these atomic clouds better to determine even more far-reaching data. For example, interactions between the particles can still be changed in a very targeted way. In this way, the quantum simulator can recreate physical situations that are so complicated that they cannot be calculated even with supercomputers. The quantum simulator thus becomes a new, additional source of information for quantum research, in addition to theoretical calculations, computer simulations, and direct experiments. When studying the atomic clouds, the research team hopes to come across new phenomena that may have been entirely unknown up to now, which also take place on a cosmic, relativistic scale, but without a look at tiny particles that might never have been discovered. And this is a professor of space physics, advanced mathematics, computer science, and later research. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.